Hi everybody, this is Dr. Hammond on notes for Physics 2500 Intermediate Mechanics at the University of Windsor. I'm going to continue today to talk more about first order solvers. Um, so these slides that I have will be discussing the exact solutions that we can get for certain first order differential equations and how we can set up some different home-built solvers to solve these things, and I will finish with discussing a built-in ordinary differential equation solving routine. So for a first-order differential equation, something we can look at that is slightly more complicated than just, velocity being the integral of acceleration, or a ball falling or a ball flying through the air, is if we have some drag that's proportional to the velocity. So we're going to say that we have this ball and it's flying through the air, and this first instance we're going to say there's no gravity. So this thing is just flying through the air with some initial velocity, and then there's this drag force that has some constant of drag mu, and the force is proportional to the velocity. So we set up the Newton's equation. So Newton 2 is mass times the derivative of the velocity with respect to time is equal to negative this constant times v. Or we can rearrange this so that we get dv by v is equal to negative mu over m dt. Now you should know where we're going with this. We have a derivative in velocity, we have a derivative in time. All the velocities on the left-hand side, the time is on the right-hand side, so we integrate this. Now we can use definite integrals. So we're going to integrate from our initial velocity, so this ball is initially flying through the air with v naught, and so our initial velocity is v naught, and we integrate up to some velocity as a function of time. And so on the time side, we integrate from t equals 0. We're just saying that the initial time is at 0 and it goes up to some time t. And of course, mu and m are constants here. So we can integrate this. The integral of dv over v is of course log v. And so since this is a definite integral, we got log v over v naught. And that is of course equal to negative mu over m times t. So we can take the exponent of both of these sides. We get v over v naught is equal to the exponent of minus mu over mt, or v of t is equal to v naught minus mu over m times t. So what does that tell us? So we have an exponential decay of the velocity. So this thing starts off at t equals 0 with v naught, and then as time progresses, this ball will slow down an exponential amount. So we already kind of know what this is going to look like. This is nice because this is basically the simplest case for drag. Let's look at the next case, which is when we actually have terminal velocity. So in the previous case, we didn't have any added source term. So that was a homogeneous differential equation. And when I say homogeneous differential equation, I mean basically all terms in v can go onto one side of this equation, and anything that's not a function of v can go on the right-hand side, and that's going to be equal to 0. Whereas in this case, what we have is we now have our mass times acceleration, or mass times the derivative of velocity with respect to time, is something that's again proportional to velocity, but now we have this source term, this inhomogeneity in our differential equation, and that's due to gravity. So this inhomogeneity, or the fact that we have an inhomogeneous differential equation, means that we have a source term. This source term is some kind of like source for energy or something like that, some driving term in our in this function. And that source term is of course going to be gravity, because that's something that's not dependent on the velocity. So if you want to find the analytic solution, what you do is, this is kind of a common trick. You can make a substitution. So you call u is equal to whatever's on this right-hand side, or we divide by m, so we just have dv by dt on the left-hand side. And so it's g minus mu over m times v. And so that is now this function u. And we take the derivative of u, and so that gives us negative mu over m times dv. But we had dv and we had v. So what you need to do is now substitute what v is in terms of u and what dv is in terms of du, and you put that back together, and what you get is an integral that looks the exact same thing as this, but instead of it being dv over v, this is du over u, and you're integrating from u naught to u. Now, of course, we could start with some initial velocity, but we'll take the assumption that we've dropped this thing, from a certain height, and we've let it go from rest. So we're going to say that v naught is equal to 0. And so then what we get when you make this substitution is you get your analytic expression is that your velocity is mg over mu times 1 minus e to the negative mu over m times t. So the difference between this equation, this solution to the inhomogeneous differential equation, and the solution to the homogeneous differential equation is, of course, the fact that there's some source term here due to the gravity. So you still have this exponential decay, but instead of this exponentially decaying to 0 as you had in the previous case, in this case, this exponentially decays, this exponentially decays to 0, of course, but it's 1 minus that. So this will eventually reach 1. And so that means that as t goes to infinity, this reaches mg over mu. So the there ends up being a terminal velocity that's mg over mu, as opposed to in the previous case, where the terminal velocity, or the velocity when t goes to infinity, is 0. So that's the difference between having a source term and not having a source term. So that's the analytic expression for linearly proportional drag with gravity. So, and I'll talk about a third case where we have a rocket flying through an interstellar cloud. So if you remember this case from back when we did this, I think in January or something like that, we had to find that the drag force was going to be proportional to the velocity squared. So typically drag has to be measured as some kind of some kind of function of velocity, and it highly depends on the shape. It highly depends on the density, like atmospheric density, things like that. It turns out that drag typically is somewhere between proportional to velocity and proportional to velocity squared. And sometimes there's even some kind of coefficients that depend on the velocity. So as it goes faster, it's more dependent on the velocity squared, and as it's slower, it's more dependent on velocity. So anyways, if we have a drag that is proportional to the velocity squared, as we have here, then we get this differential equation of m dv by dt is equal to negative mu v squared. So of course we can divide by m, so we have, and then bring the dt over to the right-hand side and the v squared to the left-hand side. So we get dv by v squared is equal to negative mu over m dt. Again, we integrate, but the integral of 1 over v squared, instead of being the logarithm, the integral of 1 over v squared is, of course, negative 1 over v. So then what we get for our solution is the v of t, this velocity as a function of time, is our initial velocity, this initial rocket flying through space, divided by 1 plus mu over m v naught t. All right. So the interesting thing about this, maybe you haven't recognized it yet, is if we integrate here, so this velocity, you could probably do this in your head. You integrate velocity to get position. Then what you'll get is still some kind of exponential function. And so that means that as t goes to infinity, our x will actually reach some finite value. However, in this case, what we have here is if you integrate this again to find position, that if you integrate this, maybe it's not quite so easy to do in your head, but it's the same thing as what we had here was, and here as well, in fact, that we'll have some kind of derivative of something over that something. And so what we have here is we'll be integrating dt over something that's proportional to t. And so in x, this will actually go as the logarithm of t. And so what that means is that if you truly had the force of drag being proportional to velocity squared forever and always for all velocities, then this object actually never comes to a complete stop, because x as a function of t goes as the logarithm of t, and there's no upper bound on the logarithm function. And so that means that obviously this proportionality to velocity squared can't be true forever and always, although this is what we derived for a rocket flying through space. So that's why I say that for very slow velocities, this changes to just being proportional to velocity. All right, so this is our analytic expression for velocity as a function of time. So we've been able to solve these first order differential equations. You'd think that the next case would be what happens if we have an inhomogeneous differential equation. Well, that becomes a little bit tougher. So I'm just going to leave it at these three cases, and we'll actually do the next case, the inhomogeneous differential equation with a drag coefficient that's proportional to v squared in the numerical solution, which I'll be getting to in the next lecture. All right, so what does this look like in terms of coding? So what we want to do is have, we define our derivative of our velocity. So we define this function in Python as v dot, so v dot being dv by dt. And it has a, the variable that we want to integrate over t, and the thing that we want is the velocity. And so what we have to return is g minus um. So um is mu over m. G minus mu m times v, where this would be our differential equation of m dv by dt is equal to mg minus mu v. So what we're returning is dv by dt, so that's g minus mu over mv. And basically what we're saying is x prime or x dot is equal to this function of t and x of t, or I guess more specifically in this case, v dot is equal to f of t and v of t. Okay, so as we discussed in the previous lecture, we have Euler integration. And so what we can do is actually just literally take what that derivative is and find the next step. And so we have x of n plus 1 is equal to x of n plus the delta t, this time step that we've created in our array, times f of tn and xn, where, as we just said, f of t and x is going to be x dot, or these are just general functions, and so what we want is, in this case, v. And so whatever we're returning here. So what we can do is just say v of our next step, so I plus 1 is going to be our current velocity plus dt, this time step, times v dot, where we've defined v dot is our derivative of v with respect to t. And then we just put this in the array, and then what vi was, so this previous velocity. So that's the simplest way to do it, but as I've mentioned, Euler integration is in fact the worst way of solving these things. It's easy to do, which is why people still kind of use it, but don't. It's really bad. And I'll give you an example in the next lecture when we're actually running the code of how bad it gets. For midpoint integration, it's not too much more difficult. Because we've defined this function, all we need to do is say that our next point is our current point plus delta t, just like we had before. And then we just have to put this in the function of our t, of our current time step, plus 1/2 of this dt. And our current spatial step plus 1/2 dt by 2 times this derivative that we already have. So what does this look like in terms of code? Well, we just say for I in range 0 to n minus 1. So our v of our next step is our current step plus dt, so this time step, times v dot. And so what's in our v dot? We have, the arguments of our v dot are the current time plus 1/2 of the time step, and the position and the velocity is this current velocity, same thing that we have here, plus 1/2 of our time step times v dot at our current time step. And so we already know this, we already know this, and we already know this entire array, and so we can just stuff that in together, and that gives us our next velocity position, or next velocity at that time. So it's not too much more complicated than simply using the Euler, and I have a little plot here that shows the difference. So if you're looking at this inhomogeneous differential equation and solving for that, the exact solution is given in black. The midpoint integration is given in red. You can see that they're fairly close, but you can see how sparse this this array is. But you can see Euler integral is quite different. It basically follows the same shape. So that's the thing with Euler. It kind of gives you like a 0th order guess as to what this thing is going to look like. And in fact, that's what the midpoint integration uses, right? It kind of uses Euler as like the first kind of guess. So you get kind of the right shape, but it's not exact. It's not very precise. I'm also going to talk about the RK4 routine. So this is called the Runge-Kutta routine, and so it uses a 4th order integral. So again, what we have is this derivative is going to be equal to some function, and so what we have to do is calculate this 4 times. So if you notice, the first this first k this first integral is delta t times this function, and this function is this derivative. So that's exactly what Euler integration is, or the same thing as the first step in midpoint integration. We have k2, which is delta t times the function at 1/2 step in the future, and plus, and the second argument is going to be our current value plus 1/2 of k1, so which we just calculated. Now, if you're paying close attention, these first 2 steps are in fact what the midpoint integration is. So the first step is Euler, the first and second step are midpoint integration. And so basically what RK4 is uses 4th order routine. So instead of just having these first 2 steps, we then have a 3rd step, which is exactly the same thing, but we just have, instead of having the argument being 1/2 of k1, the argument is 1/2 of k2. And then the 4th step is the full time step at the next interval, and so we have t plus delta t and xn plus k3. So k3 has been calculated from the previous step. So now we have 4 steps. So the nice thing about this is that we've calculated this 4 times as opposed to Euler, which only needs to do 1 calculation, and midpoint, which needs to do 2. So it's a lot more calculations per step. But as you can see, the error decreases as your dt to the 4th power. So instead of Euler, where the error grows as dt, and so that means you can take nt cubed fewer steps. So if you had to take 10,000 steps before for Euler integration, you can get the same error with 10 steps. I think that math is right. Correct me if I'm wrong. And then to get the next step, what you do is it's the current step. This should be xn, not yn, plus 1/6 of all of the sum of these. So k1 plus 2k2 plus 2k3 plus k4. So you've calculated k1, k2, k3 by k4. You put them together with these coefficients, divide it by 6, and you add it to the previous step. So I'm just going to correct this thing because this is bugging me now. So this should be written like that. Now, if we actually give an example of this, looking at the same case that we had before, midpoint, you can see that it's slightly off, but the difference between the exact solution and RK4, they're basically indistinguishable. And so RK4 is a fairly standard solver because the error is quite small, but it's still quite a quick solver. I'm going to finish off these slides by talking about the built-in solver. And so this is set up slightly differently from how we set up the previous derivatives. So instead we define a function, which is again just the derivatives, but you put in the order of the velocity and time. I've seen on some forums that you can put it still as time and velocity, but it seems like on my version of Python that I need to define the function as the function that I want to return, or the function that I want, and the variable that I'm integrating over. And then again, you can just return this differential equation, and so in this case, this is the simple drag that's proportional to velocity. And now when you want to solve it, you call some function, your solved function, and you call it with ODEint. And this is the built-in solver routine, and you call your function with that. And then because you've defined, well, I guess the ODE solver expects it to the function, and then your initial conditions, and then your variables, and then later on I'll be talking about what happens if you want to pass in parameters. But in this case, we don't have any parameters, so we just have the ODE solver is called by putting in the function and the initial velocity and the time that we're integrating over. And then this just returns a one-dimensional array, and so we'll just call this velocity from the built-in solver is just going to be this array. If you do this for multiple, for higher order derivatives, as we'll be talking about in a future lecture, probably next week, this will return as many dimensions in this array will have as many dimensions as we have derivatives. So if we're also solving for x, then this would return a two-column array. And so this would p-soln colon comma 0 would be for velocity, and colon 1 would be for x. Actually, that might be backwards. But one of the arrays will be for position, one of the arrays will be for velocity if we're solving for second order differential equation. But the returned array is the integral, and so this is the built-in solver. And so for the next lecture, I will be discussing how to use these things in Python.